Imagine a world that speaks in only two words: yes or no, on or off, 0 or 1. This is the world of digital electronics. It's a world built on the backs of tiny electrical components that process and transmit information in the form of these binary digits. These digits, 0 and 1, represent the presence or absence of electrical signals, like a light switch that can be either on or off. This binary language is the foundation of all modern computers, smartphones, and countless other electronic devices. But how does this simple system of zeros and ones give rise to the complexity we see in our digital world? The answer lies in the ingenious arrangement of logic gates, the fundamental building blocks of digital circuits. These microscopic components act as the decision-makers of the digital world, dictating the flow of information based on the binary inputs they receive. Like tiny traffic controllers, they direct the movement of electrical signals, determining the ultimate outcome of complex computations. In the realm of digital electronics, everything boils down to two voltage levels, high and low. These two levels are the fundamental building blocks of all digital systems, forming the basis for the binary language that computers and other digital devices use to communicate and process information. These levels correspond to the binary digits 1 and 0, respectively. The binary system, with its simplicity and efficiency, allows for the representation of complex data and instructions using just these two digits. A high voltage, typically represented by a positive value, signifies the presence of an electrical signal, like the flow of current through a wire. This high voltage state is crucial for signaling the on condition in digital circuits, enabling the transmission of data and the execution of commands. Conversely, a low voltage, often represented by 0 volts or a negative value, indicates the absence of an electrical signal. This low voltage state is equally important, representing the off condition and ensuring that digital circuits can distinguish between different states. Think of a light switch. When the switch is flipped on, the circuit is closed, allowing electricity to flow and the light to illuminate. This simple action mirrors the binary concept of on and off, where the closed circuit corresponds to a high voltage or a binary 1. This on state corresponds to a high voltage and a binary value of 1. In digital electronics, this state is used to represent the presence of a signal, enabling the performance of various operations and the execution of tasks. When the switch is flipped off, the circuit is broken, interrupting the flow of electricity and plunging the light into darkness. This action is analogous to the binary concept of off, where the open circuit corresponds to a low voltage or a binary 0. This off state represents a low voltage and a binary value of 0. In digital systems, this state is used to indicate the absence of a signal, allowing for clear differentiation between different conditions and states. This simple binary system, with its two distinct voltage levels, forms the bedrock of digital electronics. It is the foundation upon which all digital communication, computation, and control are built, enabling the creation of complex and sophisticated digital devices. By manipulating these levels, logic gates can perform a variety of logical operations, processing information and making decisions that drive the functionality of our digital devices. These gates are the fundamental components of digital circuits, enabling the execution of complex algorithms and the processing of vast amounts of data with remarkable speed and accuracy. Logic gates are the workhorses of the digital world, tirelessly processing information and making decisions based on the binary inputs they receive. These tiny electronic components act like digital traffic lights, directing the flow of electrical signals according to predefined rules. Each type of logic gate has a specific function, determined by its internal circuitry and represented by a truth table. A truth table is a simple chart that outlines all possible input combinations and their corresponding outputs for a given gate. By understanding the behavior of each gate, we can begin to unravel the complexity of digital circuits. From simple tasks, like inverting a signal, to more complex operations like adding binary numbers, logic gates are the unsung heroes of the digital age. They are the fundamental units of computation, enabling the creation of everything from basic calculators to sophisticated artificial intelligence systems. Section 4. The AND gate. A digital intersection. Imagine two roads intersecting, with a traffic light controlling the flow of vehicles. This intersection is a critical point where decisions are made based on the signals from both roads. The light will only turn green if both approaching roads have a green signal. This ensures that traffic flows smoothly and safely, preventing accidents and confusion. This is analogous to the behavior of an AND gate, a fundamental logic gate that outputs a high signal, or 1, only when both of its inputs are high, or 1. The AND gate is a crucial component in digital electronics, used in various applications from simple circuits to complex computing systems. The AND gate can be thought of as a digital AND operator. It performs a logical conjunction, meaning it combines two input signals and produces an output based on their values. Just as the word AND connects two conditions that must both be true for a statement to be true, the AND gate requires both of its inputs to be high for its output to be high. This principle is fundamental in digital logic design, ensuring that specific conditions are met before an action is taken. If either input is low or 0, the output will also be low or 0. This behavior is consistent and predictable, making the AND gate a reliable component in digital circuits. This behavior is summarized in the AND gate's truth table, which lists all possible input combinations and their corresponding outputs. The truth table is a valuable tool for engineers and designers, providing a clear and concise way to understand the gate's operation. The truth table clearly shows that only when both inputs are 1, the output is also 1. This reinforces the concept that the AND gate requires both conditions to be true for a positive result. In all other cases, the output remains 0. This simple yet powerful logic is the foundation of many digital systems, enabling complex decision-making processes and efficient data processing. Section 5. The OR gate. A digital reunion. Unlike the AND gate's strict requirement for both inputs to be high, the OR gate is more lenient, outputting a high signal, or 1 if at least one of its inputs is high, or 1. This flexibility makes the OR gate a fundamental building block in digital electronics, allowing for more versatile circuit designs. This behavior can be likened to a reunion of friends, where the presence of at least one familiar face brings joy to the gathering. Just as a single friend can light up a room, a single high input can activate the OR gate, making it a symbol of inclusivity and warmth in the digital world. The OR gate acts as a digital OR operator. It plays a crucial role in decision-making processes within circuits, enabling systems to respond to multiple conditions with ease. Similar to the word OR connecting two conditions where at least one must be true for a statement to be true, the OR gate only requires one or both inputs to be high for its output to be high. This logical operation is fundamental in programming and circuit design, where multiple pathways can lead to a successful outcome. Only when both inputs are low, or 0, will the output also be low, or 0. This ensures that the OR gate can effectively filter out false conditions, providing a clear and reliable output. The OR gate's truth table confirms this behavior, showcasing that as long as one input is 1, the output will also be 1. This table is a simple yet powerful tool for understanding the gate's operation, making it easier for engineers and students alike to grasp its functionality. Only when both inputs are 0 does the output remain 0. This clear distinction between high and low states is what makes the OR gate so reliable in various applications, from simple circuits to complex systems. This forgiving nature makes the OR gate useful in situations where a positive outcome is desired if any of the input conditions are met. Its ability to provide a high output with minimal requirements makes it an essential component in creating flexible and efficient digital systems, ensuring that operations can proceed smoothly even when not all conditions are perfect. Section 6. The NOT gate, a digital inverter. The NOT gate is the simplest of the fundamental logic gates, acting as a digital inverter. Just as its name suggests, it takes a single input and produces the opposite output. If the input is high, or 1, the output will be low, or 0, and vice versa. Imagine a light switch with its wiring reversed. Flipping the switch up turns the light off, while flipping it down turns the light on. This counterintuitive behavior is the essence of the NOT gate. It flips the script, transforming a 1 into a 0 and a 0 into a 1. The NOT gate's truth table succinctly illustrates this inversion. With only one input, there are only two possibilities, 0 or 1. The output will always be the opposite of the input, effectively negating the original signal. This simple yet powerful function makes the NOT gate an essential component in many digital circuits.